Hello everyone, in today's video I will be showing you how to drill micro holes using electric discharge machining. So this is in the thumbnail of the video. This is going to be in the thumbnail of the video as I'm making this. Here's my hair for reference of how small holes with this type of machining can achieve. Of course, even industrial machines can achieve probably even better results, smaller holes than this. But yeah, and so I'm gonna take off my macro lens here, and yeah, zooming out, you can get a bigger perspective of how big it is. Look at that. It's very small, very tiny. So this is the circuit diagram if you choose to replicate this for yourself. You'll need a 60 volt or higher power supply. The way I accomplished this for my setup is I used a 30 volt power supply, and I use a DC to DC converter, which allows me to get 60 volts going to a series of resistor in series with to limit the current, which goes to a capacitor. The positive goes to the electrode, and the workpiece is grounded. Over here I have a switch, but what I ended up using here, I did not end up using, I was thinking of using a MOSFET or an IGBT, but I decided on using a relay instead, but I am still controlling it using an Arduino. You could also use a MOSFET or an IGBT, both will work, and you can use the PWM signal from the Arduino to control it. And that's pretty much the setup. Oh yeah, and the lowering stage for the electrode is just a servo motor. But other than that, there's nothing much to it. So this is the relay. It's a solid state relay. It's rated at 60 volts, which is just perfect for what we're doing. And I believe the current rating somewhere around 100 amps, which is also good because we're literally going to be short-circuiting the power supply. And that's connected to an Arduino, which has a simple script that I wrote, and basically all it does is modulate the sparks. So you can turn on the sparks for a period of time, turn it off, turn it on, turn it off, turn it on, and so on. And I can change the values by just changing the code, and yeah, and this right here, so this just stands for the load and source. It's really weird how this works. So when you're connecting it with an AC power supply, it doesn't work. It doesn't really matter which way you put it, but over here we have, it says negative and positive here, but that, I don't really know what that means. How you actually connect it is you connect the wire going to your load on this end and your source on this end, and that's how you're actually supposed to connect it for a DC solid state relay. The Arduino I'm powering using this barrel jack adapter connected to a 9 volt, so that I don't have to plug it into my computer to run the code. The resistor is actually a heating element for a 3D printer. Heating elements are basically resistors, and resistors are basically heating elements. Essentially, it's just a wire that gets hot, and this has approximately 11 ohms of resistance. Here is the lowering stage for the EDM machine. It's just a servo motor with a special mount that I 3D printed using a CAD, my own CAD design. And I can control the servo like this to lower it. And it's just mounted with some very strong sticky tape. And the mount actually turns it into somewhat of a linear actuator. So, yeah, very nice. And this is all mounted on a drill stand. The bottom here is just a piece of wood, because I'm gonna be putting water, and there's some mounting holes here, so I don't want the water to drip on my carpet, so I just added this piece of wood. And that's pretty much it. Here's a simplified explanation of what's going on. You have an electrode, usually made from brass, copper, or graphite, from what I've seen, and it's slowly lowered to the workpiece until a spark occurs. All it's doing is maintaining this gap, and the sparking that occurs will slowly erode away the workpiece more than it will erode the electrode. Eventually, you'll be able to keep on doing that until you actually drill into the metal. So no actual pressure is applied, like such as when you're using a drill, because you're actually trying to maintain a gap between the electrode and the workpiece, which makes it easy to drill in very weird shapes and hard metals that usually wouldn't be possible with conventional methods. If you've ever tried discharging a capacitor onto a piece of metal, you've actually done electrical discharge machining. If you look closely, you'll see there will be two craters left behind where the metal has vaporized. The more keen-eyed observers will notice that the actual micro holes that I've drilled here is very small when compared to the actual electrode that I used. Right? So how is it possible to drill a smaller hole than the actual electrode diameter? And that's because I used a very simple trick. Now, I wouldn't have to use this trick if I actually had a smaller diameter electrode, but I don't. So what I did was, you can see what's actually happening here. The actual hole is the same size as the electrode. But what I did to make the hole smaller, I didn't let the electrode go all the way through. Instead, I only let it penetrate a tiny area, and that's how I got it smaller than the actual electrode. If I let the machine run for longer, then it would go all the way through, but then it would leave a bigger hole, which I thought it would be cool to have a micro hole instead for this demonstration.